Okay, we're going to go through the 4.1 homework. Number one, explain the difference between an absolute minimum and a local minimum. So let's just get straight to the answer here. A function has an absolute minimum at x equals c if f of c is the smallest function value on the entire domain of f, whereas f has a local minimum at c if f of c is the smallest function value near c. So the difference is between where it's the smallest value. If it's the smallest value on the entire function's domain, then it's an absolute min. If it's only the smallest value in a small neighborhood near that point, then it's a local minimum. Okay, use the graph to state the absolute and local maximums, minimum values of this function. So let's start by looking for the, well, you know what? I think what I'll do is I'll work through this from left to right. So right here, this point on the left is not the lowest point on the graph because there's more points over here that are lower. As I move up here, I get what appears to be a maximum, except for the fact, a local maximum, except for the fact that there's a hole there, so that cannot be a maximum. However, at this point is locally the smallest point. So if we just look kind of like in this little area right here, well, you know what, I'll do it this way. If we just look in this little neighborhood right around here, that point right there is locally the lowest point. So what I will say is that I have a local minimum value that happens at, let's see, there's the origin, at x equals 1, so at f of 1, and the value there is 1, 2, 3. Okay, there we have a local minimum. Now moving back along the function, I come down, and then here's another lowest point on my graph. That happens at 2 for x, spits out, let's see, 2. So I have another local minimum at f of 2, and the value is actually 2. Moving up the graph, I have here a maximum point. It's a local maximum because it's the highest point locally. That happens at, let's see, 3, 4 at f of 4, and the value there is 5. But notice also that at this point is the highest point that the graph ever reaches, so that's also my absolute maximum. And then as I move along the graph here, I have a little point down here that's going to be locally the smallest point. That happens at 5, let's see, at f of 5, and the value of the function there is 3. And then I move up here, this point right here, it is locally, so if we look in this little neighborhood right around here, it is the highest point of anything around it. So we have a local maximum at f of, let's see, 2, 3, 4, 5, 6. At f of 6, the value there is 4. And then we move along the graph, and we get to this point. This looks like the lowest point on the graph, except there's an open hole here. So we never actually get to a point. We just get closer and closer to 1. We never get there. So we do not have an absolute minimum value. Okay, sketch the graph of a function f that is continuous on 1, 5, has the given properties. So here is the graph. We have an absolute maximum at 5. We have a local minimum at 4. We have a local maximum at 3. We have an absolute minimum at 2. And then the function, of course, is defined between 1 and 5, so it's defined on that entire interval. Okay, find the critical numbers of the function. So to find critical numbers, all we need to do is take the derivative, figure out where the derivative is 0, and where possibly the derivative is undefined. So I take the derivative here. The derivative of this is 3x squared plus 6x minus 189. And then, that's this right here. What we do is we factor out a 3. So if we factor a 3, we get this. And then we take these 3 terms here, and it's quadratic. We factor it. It turns into these 2 factors. We set each of those equal to 0. Set x plus 9 equal to 0. Set x minus 7 equal to 0. We get 2 solutions. They are 7 and negative 9. We make sure that those numbers can go into the function. That, in other words, they're in the domain. And since this is a polynomial function, we can plug any numbers into this, so those two numbers will work. Also, we have to look at where the derivative may not be defined, so where it's undefined. But in this case, the derivative is a polynomial. Polynomials are defined everywhere, so we don't have to concern ourselves with that. Okay, this problem is pretty much the same. We take our function, we take its derivative, which is here, factor out a 24, take these three terms, factor them into these two factors, set each of those equal to 0, and we get these two. Again, making sure that they are in the domain. Well, this is a polynomial, so those numbers will work. We do not have to look at where the derivative is undefined. I'm just going to put UND. Because it's a polynomial, we don't have to worry about it. The derivative is a polynomial. Okay, same thing here. I won't work through that one because that's pretty much the same. Oh, you know what? I think this one turns out quadratic formula, so let me see. Take the derivative, 12x squared plus 2x plus 4. We set that equal to 0, and we wind up having to try and solve this. It will not factor, so we have to use a quadratic formula. Quadratic formula says that the solution to this quadratic would be x equals negative b plus or minus square root b squared, which is 4, minus 4 times a is 12, times c is 4, all over 2a, 2 times a, which is 12. What we'll notice here is that these three numbers together, when we subtract it from 4, it's going to give us a negative number under the root, which means there's no real solution to this, which means there's no critical numbers. So this particular function does not have any critical numbers. Okay, for the next one, this one's a little tricky. Let me bring up the solution so you can see, instead of having to write all this out. You have to know a little bit about the absolute value function, how it's defined. So if you want to say the absolute value of something, the absolute value of 5t minus 1, what you're going to do is break that up into a piecewise function. So as long as what's in there, 5t minus 1, is a positive number or 0, then it spits out exactly what it was. But if that 5t minus 1 turns out to be a negative number, then you want to take that negative number and you want to make it negative. Negative and negative would be positive, so it'll spit out the positive answer, thus giving you the absolute value. So now what I do is I take the derivative on top and bottom, both of these. The derivative of 5t minus 1 is 5. Derivative of 1 minus 5t, which is what you get when you distribute the negative 1 through here, is negative 5. So as you can see, at certain values, when t is bigger than 1/5, that all they did there is just solve that and solve this. When t is bigger than 1/5, we have a derivative of 5. When t is less than 1/5, we get a derivative of negative 5. So let me draw a picture of what's happening here. For the derivative of this, g prime, here's 1/5. We get 5, sorry, I think it was 5 if we're bigger. And we get negative 5 if we're smaller. So it looks like that. That's what the derivative looks like. And what you'll notice is that the derivative has a jump in it, a break. So we have a place where the derivative is undefined because it jumps. So that happens at t is equal to 1/5. Just double check it was 1/5. Yes, okay. All right, for this one, find the critical numbers. So what we're going to need to do is do a little bit of quotient rule. Derivative of the top is 1 times the bottom minus the derivative of the bottom times the top all over the bottom squared. Okay, now when we clean up the top, the 1 goes through here. We just get y squared minus 3y plus 3. We go ahead and distribute here. We get 2y squared, but then we're going to subtract it. So minus 2y squared. We have minus 2y, but then we're going to subtract it, so plus 2y. We have negative 3y, but we're going to subtract it, so plus 3y. And then we have plus 3, but we're going to subtract it, so minus 3. And that's all over the bottom squared. Things on top clean up. Let's see, we have y squared. Oh wait, y squared, negative y squared on top. That's these two. And how many y's do we have? These y's cancel, so plus 2y. And then these 3's cancel. So those 3's cancel, and so that's all we get on top. On bottom we have that denominator squared. We set that equal to 0. So if we set that to 0, all we have to do is look at the numerator and say, when is that 0? So I take that and I factor out a y. I'm left with negative y plus 2 equals 0. Set each of these equal to 0, you get y is 0. Set this whole factor to 0, you get y is equal to 2. Now we got to make sure that there's not a possibility that the denominator here can be 0, because then we'd have undefined. So if we try and figure out when that's 0, we could take it, set it to 0, and use quadratic formula and get y equals negative b plus or minus square root b squared minus 4 times a times c. But this number in here is negative, so we can't get a real solution there. So it's not possible for our denominator to be 0. Therefore, the only two critical numbers we have are 0 and 2. This problem works out pretty much the same way, so I don't think I'll go through that. Let's see if there's anything special here. Yeah, so derivative of the top times the bottom, all that, clean it up. You get a quadratic on top. When you set that quadratic equal to 0, you get these two numbers. And also the denominator can never be 0, right? Because p squared plus 2 is always a positive number. So the only critical numbers you have are these two numbers right here. The only difference between this one and the one I just did is ours, the one I just did, this was a little easier to solve. On this problem, you have to do quadratic formula. Okay, let's look at this one. This one's a little tricky. So I first need to find the derivative of capital F, which is going to be, I'm going to use product rule. So here's product right between there. Derivative of x to the 4/5 is 4/5. X to the, I subtract 1, negative 1/5. Then times the other function, x minus 9 squared. Then plus product rule, derivative of x minus 9 squared is chain rule. 2 comes out, x minus 9 to the first power. And then derivative of what's inside, but derivative of what's inside is 1. Then times the first function, x to the 4/5. So I need to figure out when this is 0. So this is a little tricky. Let me rewrite this first piece here. This is the same as 4 x minus 9 squared over 5 x to the 1/5. So bringing that x to the negative 1/5 down, and then it joins with the 5 that was out here. Then plus, let's see, 2x minus 9 x to the 4/5 all over 1. Now I'm doing that because I want to set it to 0. So I want to get a common denominator. So what I will do is I will multiply x to the 1/5 here into 5, 5x to the 1/5 on top. When I do that, I get my 4 times x minus 9 squared plus this 5 and this 2 become a 10. X to the 1/5 times x to the 4/5. We add the exponents. 1/5 plus 4/5 is 1. So I just get x. And I still have x minus 9. And then all of this over my common denominator, 5x to the 1/5. Then, before I set this to 0, I'm going to notice I have an x minus 9 here and x minus 9 here, so I'm going to factor one out. I'll be left with a 4 here, and then one of these x minus 9s, so I have a 4 times x minus 9. And then when I factored out the x minus 9 here, I'll be left with a plus 10x. And then all of that over 5x to the 1/5. All right, I need some more room here, so let me go up here. So going up here, I have x minus 9, and then I have distributing my 4 through. I get 4x, it's going to join the 10x, that's going to be 14x. And then I have negative 36 all over the bottom. Okay, so now what I need to do is set this thing equal to 0. So when I set the top to 0, set that to 0, I get 9. Set this to 0, you get x is 36 over 14. Divide everything by, let's say, 2, and you get 18 over 7. So these are two critical numbers. And then we have to look at what might make my denominator 0. And that would happen if x is 0. So x equals 0 is the other critical number. My phone is about to die. And I don't know why. Let me go. Let me plug this in real quick. Let's take a look at this next one here. Find the critical numbers of this function. Oh, wait, hold on. I wanted to check that, make sure I didn't miss anything on that. What the heck? X minus 3. Did I write that problem down wrong? Oh, it's a different problem. X minus 3. Sorry. Well, mine's going to be a little different. All right, that could be an issue. Let me do something real quick. I need these problems to match. So go to a new page. Bear with me. All right. So I'm going to pick up actually doing this problem now. So now I'm on number 11. So now I want to take the derivative of this to find the critical numbers. All right, power rule. Derivative of x to the 1/5 is 1/5. Subtract 1, so negative 4/5, x to negative 4/5. The other one, I bring the negative 4/5 out. It multiplies times negative 1. It becomes positive 4/5. X to the, when I subtract 1 from this, I get negative 9/5. And now I need to figure out what the heck this is. So this is 1 over 5x to the 4/5, bringing it down to the bottom, plus 4 over 5x to the 9/5. I need to have the same denominator, so I'm going to multiply x to the 5/5 here, x to the 5/5 here, so that when I multiply these two, I add the exponents. 5/5 plus 4/5 is 9/5. But this is really just a 1, so I'm really just multiplying or putting an x on top there. So x, I still have the plus 4 up top, over the new common denominator, which is 5x to the 9/5. Now I want to know when that's 0. So when is the top 0? That happens at negative 4. And then when is the bottom 0? That happens at x equals 0. However, we do have an issue because the original problem, this part is 1 over x to the 4/5. And therefore, x cannot be 0 or else the original function is not defined. So even though I got a critical number of 0, I'm going to throw it out. The only critical number I'll have is negative 4. Just make sure that these match up now. Make sure I'm getting the right solutions here. Yeah, okay, so things match now. Got to do a quick pause. Maybe. All right, for this next one, we're trying to find the critical numbers of this function. So let me take the derivative. Got some trig stuff here. So derivative I'll just say f prime. Okay, 4 times that, so it's negative 4 sine theta. And on this one, we need a little chain rule. So 2 comes out, so 4 sine theta to the first power, but then times the derivative of sine because of chain rule, which is cosine. Now this, we need to set to 0. So what I can do is I can factor out, let's factor out a negative 4 sine theta. That's because I have a negative 4 sine theta here, and I have 4 sine theta here. So what I'll be left with is a 1 minus cosine theta equals 0. So now I set each of these to 0. Now I can divide both sides by negative 4, so that's gone. So I want to know when sine theta is 0. I want to know when 1 minus cosine theta is 0, which means I want to know when cosine is 1 and sine is 0. So when does this happen? So I'm going to go to my unit circle. Remember that on the unit circle, the y-coordinate is sine theta and the x-coordinate is cosine theta. So I want to know when my y-coordinate is 0. It's going to happen here and here. So the way I say that is theta can be 0 or pi, or we can come back around and come back to 2 pi, or we could go around again and that would be 3 pi, and so we have all these answers, infinitely many. So the way I say it is n pi. Then I look to see when when cosine is 1. Cosine's the x-coordinate. That only happens here. So I could be at 0, or I could go all the way around to 2 pi, or I could go all the way around again and be at 4 pi. And there's infinitely many answers there. So I could say theta must be equal to 2 pi n. However, this answer will suffice because this gives you every pi, and this one gives you every even pi. So this list over here includes all of the answers in that list. So pi n is sufficient. Find the critical numbers here. So let me take the derivative with respect to theta. So derivative 28 theta is 28 minus 7. Derivative of tangent is secant squared theta. I want to know when that's 0. So I have when is 28 equals 7 secant squared theta. Divide both sides by 7. I get 4 is equal to secant squared theta. I take the square root of both sides. Plus or minus 2 is secant theta. And now I just remember that secant theta is the reciprocal of cosine. So if I flip 2 over 1 over and make it 1 over 2, I flip the other side over. Secant, which is 1 over cosine, will become cosine over 1, which is just cosine theta. So I want to know when cosine theta is positive or negative 1/2. So go to my unit circle again. I notice that my x-coordinate is 1/2 here. It's negative 1/2 here. And it's negative 1/2 here and positive 1/2 here. These angles are pi over 3, 2 pi over 3, 4 pi over 3, and 5 pi over 3. And what I can do is to start it at pi over 3, to get back to it, I add a full rotation. So I can say pi over 3 plus 2 pi n. That'll give me all those answers, all these. And then I could say to get to 2 pi over 3, I go here, and then I add a full rotation, or another full. So I can say 2 pi over 3 plus 2 pi n. And then so on and so forth. I go to the next one, it's 4 pi over 3. So 4 pi over 3 plus 2 pi n, full rotations. And then last one, 5 pi over 3 plus 2 pi n. So I have a lot, infinitely many solutions for my critical numbers. All right. Now, I do have to be concerned with the fact that the original function may not be defined somewhere. So remember, tangent is sine over cosine. Cosine is on the bottom. I want to know, can that ever be 0? Well, the only places that cosine is 0 are here at pi over 2, 3 pi over 2. And my answers don't show up there, so I don't need to worry about those. All right, let's find the critical numbers here. So I'm going to take derivative product rule here. 3x squared times e to the negative 8x plus derivative e to the negative 8x is e to the negative 8x times the derivative of what was up there, negative 8, times the first function, x cubed. So I'm going to rewrite this as 3x squared over e to the 8x plus negative 8x cubed over e to the 8x. These have the same denominator. I'll put them together. 3x squared minus 8x cubed must equal, or sorry, over e to the 8x. I want to know when that's 0. So I take the top, I set it to 0, factor out an x squared, left with 3 minus 8x. Set that equal to 0. I get x is 0. I get x is, what is that, 3/8. Make sure that those points can plug in over here, which they can. Do I ever have a problem with that being 0? No. E to anything can never be 0. So those are my only critical numbers. I'm going to check that one. That one seemed a little bit too easy. Okay, so 0 and 3/8. This one works similarly. Let me work it. Product rule. Derivative first one, negative 5x to negative 6, and then times the second one, natural log x, plus derivative of natural log of x, which is 1 over x, times x to negative 5. This is the same as negative 5 natural log x over x to the 6. I'm just dropping that x to negative 6 to the bottom, plus 1 over x, but then that x to negative 5 comes down, it's x to the 6th down there. They have the same denominator, so negative 5 natural log x plus 1 over x to the 6th equals 0. Now, when can the top be 0? Well, that's going to be 0 when negative 5 natural log x plus 1 equals 0, which means that 5 natural log x must equal 1. 5 natural log x must equal 1, which means natural log x must equal 1/5. And now to get x by itself, we take e on both sides. And then you get x to drop out on the left, and on the right you get e to the 1/5. So that's one critical number. The other one is when the denominator is 0, but that's going to happen when x is 0. Now we got to check to make sure these can get plugged in. E can get plugged in here, no problem, so we don't have any domain problems, but 0 cannot, because remember that's 1 over x to the 5th. I cannot plug 0 into that. So I scrap that one. The only answer is e to the 1/5. Okay, my goodness. This is a heck of an assignment. Find the absolute maximum values on the given interval. So here's what we're going to do. We're going to first find the critical number. So we take the derivative of what's here. 6x squared minus 12x minus 18. We set it to 0. Factor 6 out, x squared minus 2x minus 3. We go ahead and we factor this. X minus 3x plus 1. And then our only two answers are 3 and negative 1. So what we'll do now, because we're on a closed interval, is we evaluate the original function at our endpoints, negative 2 and 4, and then at our critical numbers, 3 and negative 1. And then whatever we get when we plug these values into the original function, the biggest one is going to be our absolute max, and the smallest one will be our absolute min. Let's just see what that turns out to be. I'm not going to go through plugging those in. Let's see. So here they plugged in negative 1. Right, we had negative 1 right there. They plugged in negative 1, they got 17. They plugged in 3, got negative 47. Plugged in negative 2, got 3. Plugged in 4, got negative 33. The smallest number we get is negative 47. That happens at 3. And then the biggest number we get is 17. That happens at negative 1. Okay, for this one, same thing. We're going to take a derivative. Got a little product rule here. And I think I'm just going to look at the solution on this. Again, got some time constraints here. All right, so this one's going to be a little bit tricky because of the derivative. It's product rule. You work out the product rule, you get this. You do a common denominator, so you multiply top and bottom here by the square root of 9 minus t squared. You get this. You simplify, you get this. On the top, you set that to 0, and then you solve that, you'll get two answers, positive and negative root 4.5. Make sure you're looking in the interval here from -1 to 3. Negative square root of 4.5 is not in this interval, so we throw it out. So only the positive square root of 4.5 works. And then in the denominator, if we set the denominator equal to 0, we get two possible answers, 3 and -3. But -3 is not in this interval. +3 is actually an endpoint, so we actually are going to test that anyway. So what I'm going to be doing is I'm going to be plugging in -1 and 3, so -1 and 3 into the function, and that positive root 4.5. And I compare the answers. I get -√8, 4.5, and 0. So 4.5 is the absolute max. -2 root 2, which is this one, is the absolute min. Work on that derivative. That's a little tricky. Same thing. Okay. Okay, so here we're going to do the exact same thing. We take derivative of this, which is this, and then we use a double angle identity right here. Cosine 2t is 1 minus 2 sine squared t. And the reason we do that is because now if we take the 8 out, we'll be left with the quadratic in sine. And so it factors to be this piece times this piece. So these three terms factor to be these two. And then I set each one of those equal to 0. So if I set that to 0, I get that sine of t is 1/2. I set that to 0, I get sine of t is -1. Sine of t is 1/2 means that on your unit circle, your y coordinate is 1/2. That happens at pi over 6. And then sine t is -1 means that your y coordinate is -1, but that doesn't happen unless you're at 3 pi over 2, so we can chunk that. We don't have to worry about that. So the only points we have to check are the two endpoints and then this pi over 6. And if you plug them all in and compare them, you'll see that at pi over 6 is where you get the max, pi over 2 is where you get the min. All right, hope that helps.